And now that sounds kind of scary, but my opinion, this is like the easiest thing we do in the semester. So take that for what it's worth. By and large, like, while it takes a little bit of like three-dimensional like visualization, it's like the actual mathematics you're doing is like really easy. It's basically like Pythagorean theorem, SOHCAHTOA, like formulas, which right on, like that's not complicated at all. What we're going to work on in this first section is we're just going to talk about some names, a little bit of light vocab, review some formulas from geometry that we might have seen, or well, should have seen. And then we'll dive into section 2, which is just kind of some application stuff. So not too bad. I'm going to ask you guys to help kind of do a little bit of light recall. So starting on the left, what's that first figure? What do we call that thing? Cube, right? That's great. All the sides of a cube are squares, right? They're all the same size squares. What's special about a square? 4 sides are equal and 4 right angles, right? Good. The next figure, what do we call that thing? That's a what? Okay, so you could call it a prism, or you could call it a rectangular solid. Would be a little bit more specific. Prism is a little bit broader because lots of things are prisms. So when you use that term prism, what does that mean? So a prism means that you have 2 faces that we call the bases that are parallel and congruent. And then any cross-sectional area that you chop, if you look at the piece that you've chopped, it's the same shape, or it's congruent to the base. Right? So if you slice that box in half parallel to the bases and you take a look at what you cut, it's still the same shape as the base, right? Everybody cool with that notion? Like when you slice a loaf of bread, you look at it and it's like the same slice. You know what I mean? Does that make sense? Sometimes it's hard to think about it in 3 dimensions. Okay. So you call all that rectangular solid or rectangular prism. Both are appropriate. What's this third thing? Pyramid. Should we be a little bit more specific than that? Yeah, so we'd call this a square pyramid because the base of that pyramid is a square. You could have other shapes on the base and still be a pyramid. So what's the thing about a pyramid other than the base? Is that all the faces are triangular, right? What about this last thing? What is that? Looks like a doorstop. You say an envelope? I mean, if you say so. Yeah, that's it. So that's a triangular prism. Again, it's a prism. You can see the 2 parallel bases there are both triangles. Everybody kind of see that? Okay. FYI, all these things that we're defining now are also defined in the lessons in words, but like, I don't think the words are going to be particularly valuable to us as much as the, just like knowing what this stuff looks like. You know what I'm saying? Like a picture's worth 1,000 words kind of thing. That's some art crossover. Woo! All right, here's another group. What's that first thing there on the left called? Yeah, that's a cylinder. How about the second thing? What do you think? It's kind of a trick question. It's another rectangular solid. Again, or you could call that a rectangular prism. That's okay to do that too. How about the third thing?
A rhombus solid.
Well, if you look here, it's kind of hard to see. That's a right angle mark down there. So that's actually still another rectangular solid. What's the difference between those two, though? Yeah, one is like straight up and down and one is like tilted, right? So the one that's straight up and down, we're going to add a second qualifier onto it. What word do you suppose we're going to add to that to indicate that it's like a straight up and down? We're going to call it a right rectangular solid because the angle that the faces make to the base is at a right angle. Like if you're building a building, you know, that's what you'd hope for, right? Nobody wants a building that's falling over. I mean, maybe you would, but I don't know why you would want it. And then we differentiate with the one here next to it. We'd call this one an oblique rectangular solid. That's the word we'll use for something that's tilting. Like the Leaning Tower of Pisa is an oblique cylinder. I think it's a cylinder-shaped building, isn't it? Art history people. Leaning Tower of Pisa, is that a cylinder or cylinder-ish?
Yeah.
I think it's cylinder-y. But it's leaning. So oblique, whatever the heck it is. I think it's like a cylinder-ish. Might be elliptical instead of a circle. I don't really know. Great. The next guy, what do we call this guy? It is another triangular prism, yeah. You could be more specific and call it a right triangular prism even, if you'd like. Sure. Everybody cool with that? And the last one here, what do we call this thing? Well, that's 5 sides, so it's pentagonal prism, yeah. But it's just another prism. What do you notice here? We have a whole page of prisms. Really, even the cylinder is like a prism with circular bases, right? Technically. What do you guys think? No big deal so far? Again, just talking about some names. Do you think you're going to have to like do some kind of matching nonsense where you have to match the shape to the name on a test? No, I'm not interested in that. You just have to, like, if they say the name in a, you know, in a story problem, be able to draw like a reasonable facsimile of the picture or whatever. That's all I need you to know the names well enough to where it's like I could draw a picture of that thing. That's all we're worried about. You know, I'm not going to be like, you got to be able to know this and like spell the name correctly or some nonsense. Like, I ain't interested in that. Maddie. And I meant Mackenzie. How come you didn't correct me when I said it wrong? Well, you should. It's your name. I'll start calling you like Poopy Pants or something if you don't care what I call you. You don't think that would bother you either? Wow. I'm going to take that. Next time you have to make something up, I'm going to write Poopy Pants on it. Poopy Pants Shirley. So that the person giving the makeup test is goes like, who the heck is this for? Yeah. They'd probably assume that anyways, right? We good? Okay. All right, so what do we got here? If I was going to name this thing, could you be even more specific? Yeah. And notice that for a pyramid, it's not the faces that are going to be perpendicular to the base. It'd be like the height that needs to be perpendicular to the base to make it a right square pyramid. Everybody's cool with that? This point up here on your square pyramid has a special name. Hi, Nico. How are you?
I'm all right.
Thanks, bro.
Thanks.
This point up here is called the apex. Again, you know Mr. Kulik, he's not going to ask you vocab questions on the test or whatever, but like if we try to give you a story problem in words and talks about the apex of a pyramid or something, you got to know like, oh yeah, that's just the point. You know, like, you know what I mean, guys? Just like functional knowledge of the vocab. We're not going to have like a vocab test in here. Get out of town. If we're in geometry and we're proving stuff, then yes, that would make sense because like you got to know the vocabulary to prove stuff. We're not proving anything in here. We're just calculating stuff. Okay. Next round of pictures. Oop. All right, picture number one. What is that? Sphere. Picture number two. Hemisphere, yeah. Global politics in play here, right? Oops. Picture number three. You knew this before. Yeah, it's still just another cylinder. And picture number four. Cone. Worth pointing out here, this point on the cone also has a special name. Still the apex, though. Everybody okay? These figures, again, shouldn't be super, like, unfamiliar, right? Sounds like things that we kind of know the names of mostly. So take a few minutes and just kind of redo some, or review some area and volume formulas. So the area of a triangle, what is that? Great. Or, if we're back a chapter, we could have also said it's not a chapter, 2 chapters. Oh, how quickly we forget. 1/2 AB sine C, right? Or, what was the other one? Square root of S times S minus A times S minus B times S minus C, where S is the semi-perimeter. That was Heron's formula from chapter 7. We got those kind of sound familiar. If you have a right triangle, which one of them is the best one? The first one, right? Clearly, since the sides of a right triangle, or the legs of the right triangle are just the base and the height, no big deal. If you have a non-right triangle, possibly the other two might be more valuable to you. How about the area for a parallelogram? Does anybody remember what that is? Put on those geometry thinking caps. It was a long time ago, but it was an easy formula to remember. It's just base times height. What's the tricky thing about that, though? The height for your parallelogram is probably not a side length unless your parallelogram is like a square rectangle or something. You guys remember that? From geometry. Here's mad props if you remember the area for the trapezoid. This one's hard to remember. Anybody remember this one? Yeah, that'll do. Good job. So again, trapezoid, you have two parallel sides. Those are the bases. We call that B1 and B2. And then the height of the trapezoid could be not a side length. I usually like to say the average of the bases times the height instead of 1/2 B1 plus B2, but you know, whatevs. So far, so good. How about the circumference of a circle? Anybody remember that formula? 2 pi r. That's good. How about the area of a circle? Yup. How about the area of the curved surface of a cone? So like think about you're holding an ice cream cone or whatever. The circle part, even though that's a round shape, is a flat surface, but the whole part you'd hold in your hand is all curved, right? So you're just talking about what's the area of that curved surface. Anybody remember this one? This is tricky. So this is pi times the radius times the slant height. So what the heck do we mean by the slant height? So this side of the triangle BDC, the hypotenuse there is our slant height. Everybody's okay with that piece of vocab there? Notice that I'm using a script L there. Why do you suppose I'm using a script L when I'm writing that? My lowercase l looks a heck of a lot like a number 1. That feels like a boo-boo waiting to happen, hence me using the script L, which doesn't look at all like a number. You know, just some common sensey stuff there. volume of a cone. Does anybody remember that?
1/3 pi r squared times the height.
Yeah, I'm going to say base time, area of the base times the height. So I use the capital letter B to represent the area of a base. And in a cone, that base is a circle, so it'd be pi r squared. But I like to just like area of base times height it whenever possible, since it just like simplifies the formula, and I use another formula to, like I nest them. You know what I mean, in my memories? So let's see. So what about the area of the curved surface for a cylinder this time? So, you have the cylinder, has a circle on top and bottom. Those are technically flat, right? But the part you'd hold when you hold your can of pop or whatever, that's all curved surface. What's that area got to be? Just the circumference of the circle times the height, or 2 pi r h. Everybody feel good here? Okay. What about the volume of a cylinder?
Pi r squared height.
Yeah, area of the base times the height, and since the base is a circle, pi r squared h. You got it. About the volume of a sphere?
4/3 pi r to the third.
Yeah, 4/3 pi r cubed. That's a weird one to derive. I can't remember in geometry. Did you guys derive that? I think when I used to teach geometry, you derived this, but it's kind of complicated to get it without calculus anyways. If you take calculus, I suspect Mr. McCaskey derives this for you when you do like volumes of revolution. It's typically a pretty standard exercise. What about the surface area of a sphere? This is a weird one to remember. So that's 4 pi r squared. How about the volume of a pyramid?
1/3 length times width times height.
Well, we didn't say that it was a square pyramid, so we better say area of the base times the height, since if it's a triangle or a pentagon or something weird like, But if it was a square pyramid, yes, that would be true. I'm going to just write it as area of the base. And in fact, the volume of any prism, pyramid should be py, is just area of the base times the height, right? For any prism. Now, if we're talking about the most common prism we run into, the rectangular prism, the base is a rectangle, so the area of the base is length times width. So rectangular prism's volume is length times width times height. Everybody feel cool there? Okay, so you probably at this point are going, aye, Mr. Kulak, that's a million formulas. Do I have to memorize all those? Well, if you look at the review packet and you look at the last page, which includes the formulas that are given to you on the test, boy, it looks like basically everything there is on there, right? You could take a look, but I think that's pretty inclusive. So, no, it's not going to be like a memorization of a million frickin' formulas, because who has time for that, right? Let's not. Everybody happy so far? So at this point, all we've done, a bunch of vocab, but really just like, can you look at a picture and tell what it is? Or like, if I tell you what it is, could you sketch me a little picture of it? Fine. Reviewed some formulas that I already know, but I'm probably going to be given the formulas anyway, so all I really have to do is like know how to plug the numbers in for the right letters. Fine. That's it for section 1. Sections 2, 3, and 4 I'm going to use PowerPoint to do because they're going to involve like a whole bunch of drawings, and like I don't trust myself to be consistently neat enough to give you a good picture. So I'm going to do these all digitally. Worth mentioning here, though, that these PowerPoints, if we go to My Notre Dame and you look at your day, if you look at the downloads section on My Notre Dame, it has the PowerPoints if you want to look at the PowerPoints later on. That's great. My suggestion to you, because of that aspect, is probably don't try to draw the pictures on the PowerPoints, because woof. You know, that's kind of a lot. This might just be a like follow along and, you know, maybe take some, you know, when we do the examples or whatever, but some of this stuff, it's just like, we're just talking, you know? Everybody's cool? Okay. So in section 2, we're going to talk about finding lengths within a three-dimensional solid. So to do that, what we're going to rely on are called calculation triangles. In general, we're going to want to find right triangles within our three-dimensional figure that we can use to find the desired segment. So for example, if we have the right pyramid here, this triangle ABC is a right triangle. So that could be considered a calculation triangle. Basically, I found some triangle that's inside of some three-dimensional figure, and if I had two of the 3 sides, I could use the Pythagorean theorem to find the third side or whatever. Everybody cool with that notion? Now, sometimes these right triangles and calculation triangles that you're going to be building are going to be really obvious. You're going to see them right away, like that one there. Some of them are kind of unexpected. You know, they're a little bit harder to visualize that it's actually a right triangle, and in fact, it looks like on paper that it's actively not a right triangle. So for example here, the pink triangle, ADE, is quite obviously a right triangle. I mean, it looks like a right triangle at just half of a rectangle. We know that's a right triangle. But this blue triangle back here, FGD, is also a right triangle. Angle G is the right angle because I know that this edge, FG, is going to intersect the face, GHDC, at a right angle. Right? We know that's how cubes work, or cuboids, I guess in this case. I guess it's probably not a cube. So this segment GD that is inside of that plane, I know is also going to be meeting FG at a right angle there. A little hard to see. Doesn't really look like a right triangle at first glance. You guys see it though? So there's our calculation triangles that are off to the side. Again, this is the kind of stuff I would probably opt not to try to draw the pictures of, because like, woof, to do all the shading and coloring and everything in there. Like, you're one heck of an artiste, but more power to you if you want to. Plus, you have the PowerPoints available for download, so you can always go back and take a look. We're just going to run through a bunch of examples of these kind of unexpected triangles right now. So if we look at this one, here's a triangular prism. The pink one, pretty easy to see that that's a right triangle. F looks like a right triangle. The blue one, though, is also a right triangle. Angle B is the right angle, even though that looks like kind of an obtuse angle from here, right? But I know, again, that because this is a prism, these two bases have to be parallel, so this side that's going in between them has to be at a right angle. So we know this angle B is a right angle. And again, you're getting this distortion. The reason this doesn't look like a right triangle is because you're taking a three-dimensional object and kind of projecting it down into a two-dimensional space. You know, like when you look at a map in your history textbook and you look at like, whoa, Greenland looks freaking huge. It's the same size as South America. The same kind of thing. You're getting a distortion. There's actually a couple different ways you can project the globe onto a map. And that one that most commonly that you see in your textbook, I think it's called the Mercator projection, where Greenland looks like gigantic. And really, if you look at land mass or whatever, it's like not really that big. It's not like the same size as South America. I think the Mercator projection is one of those things that like really over-represents like the size of Europe, which probably is like an artifact of a Eurocentric world or whatever. Anyways, I'm just rambling now. There's a whole fascinating episode of West Wing where like they talk about map projections on it. It's my favorite episode. That's me. Anyways, keep continuing on. Some more examples. So here the blue triangle is probably the easy one to see as a right triangle. It looks like a right triangle, right? The pink one, though, is also a right triangle. Angle F is the right angle. Again, decidedly does not look like a right angle in the drawing, but it is a right angle. We know that a right pyramid is going to be perpendicular to the base. So anything height intersecting with any line in the same plane as the base is going to be at a right angle. Everybody's okay with that? So again, all we're doing right now is just like running through examples to get you build up a little intuition. So when you look at these things yourself, you're able to kind of pick out right triangles. You know where to look. Okay. Yeah, so here's our two triangles. Again, I almost always am going to draw the calculation triangle outside of the figure so I can, write numbers next to it and stuff and like draw it so it looks like a right triangle as opposed to what I have here that looks weird. All right, example time. I got a couple examples here. I think I have 3 examples that we'll work through. So when doing any of these problems, my plan is going to be to sketch a picture. For the case of three-dimensional solids, usually that will be provided in the question, but if I don't have it, I'm sure as heck drawing it. Identify the calculation triangles I need to answer the question, sketch and label those calculation triangles, and then solve the triangles to figure out what I need for the question. So here we have a shoebox is 32 long, 18 wide, and 11 high. Want to calculate the length of the longest rod that will fit inside the box. So think about a box, like a shoebox or whatever. And think about if you're trying to fit the longest stick possible in there, how's that going to go? Yeah, like from the bottom back to the top of the front is kind of what we'd be saying. So like in the case of our picture, this segment AG that's going from the bottom front to the back top is going to be the longest thing we could fit in there. Do you guys see that in your mind's eye? Sometimes it helps to close your eyes and imagine it, but this is where like a little bit of like three-dimensional creativity or imagination kind of helps. So there's certainly I'm going to need to use a right triangle that involves this side AG, so the pink triangle I've drawn in here is clearly one of the calculation triangles I need. The issue, though, is I only know one side of it. I only know the height of the box. So I'm going to need to figure out AC before I can use the Pythagorean theorem to find AG. Everybody's cool with that? So I'm going to look for another calculation triangle that involves AC. I mean, clearly that's going to be ADC here, right? Should be pretty easy to look at that. And I love that one because I know two side lengths for it already. So Pythagorean theorem, yada, yada, yada. I get square root of 1348. Everybody's happy with that? So then I can plug that into my triangle AGC. This 36.7 is just like an estimate of square root 1348. It just was easier to put it into as a decimal instead of a square root symbol when I built the triangles or whatever. You notice I got a little bit of lazy left over here. So again, set up the Pythagorean theorem, and I get square root of 1469 or about 3833. Yeah.
I think I've also just found the diagonal by doing like the root of length squared plus width squared plus h squared to find the diagonal of rectangular prism.
Yes. So what Jackson is suggesting is like, hey, if I think about this as like a three-dimensional coordinate system, I could embed this as the point 0, 0, 0, and this is the point 32, 18, 11. And then use the three-dimensional distance formula to do that. You could do that as well. It would not be incorrect to do that. Although is like you're now pulling things from last chapter instead of using these geometry concepts, but not incorrect. Certainly doable. And it's nice that it's one step. Yeah. Certainly I agree. Everybody cool though? Okay, let's do one more. Actually, I think I have two more. So here we have a square base pyramid, EABCD, where the sides of the square are 12 and the height of the pyramid is 9.5, and we want to calculate the length of EC. And then we have at point M, which is the midpoint of one of the sides, want to calculate the length of EM and then explain why EC and EM are not the same. So here's my picture. Boop. Again, since we're looking for EC, I drew a calculation triangle that involves EC and involved at least one of my pieces. So the piece that I knew was the height as well as the side length. So I drew here as my pink triangle. Now again, run into the same issue where my, excuse me, I only know one of the three sides of my pink triangle. So I'm going to create another calculation triangle to find the third or one of the other two sides. Obviously here FC, because if I could find EC directly, I would just do that with a triangle. So what other calculation triangle can I use to find FC? Okay, so there's two possibilities. I could use CFD. Now, that's going to rely on a couple of pieces of prior geometry knowledge to know that's a right triangle. I know since the base is a rectangle, it's actually a square, but we know all squares are rectangles. I know the diagonals intersect at right angles, so I know that angle F there would be a right triangle. And since the base is a parallelogram, it's actually a square, but all squares are parallelogram. I know the diagonals intersect or bisect each other. So I know that FC and FD are the same length. So doing that, I could use a Pythagorean theorem and solve for FC. Everybody okay with that? That's probably not the option that I would use, but it's typically the first one somebody suggests. Nobody suggested anything here, so I just kind of dove into it. That's okay. The one that I would probably do would just be CAD. because I know this side is 12, this side is 12. And then again, since I know that the diagonals of a parallelogram bisect each other, I know that FC is just half of AC. So I just calculate AC and then divide by 2. Everybody okay with that? Again, I'm pulling some old geometry theorems, which maybe you don't remember off the top of your head, but like they all look like they're true kind of theorems, right? If you draw the diagonals for a square, they sure as hell look like they're perpendicular and bisected. You know what I mean? You don't have to prove that they are. You get what I'm saying, guys? I'm always going to like explain to you why and like cite the theorem that we talked about in our geometry class, because that's what teachers do, but I won't ever ask you to cite a theorem unless it's something pretty obscure. And I'm like, whoa, why is that true? But anyways, unless we're talking about it in class, I'll drill you about it then, but that doesn't matter. Okay, so that gives us FC. And then once we have FC, we can calculate EC just using the Pythagorean theorem again, right? And this is kind of as bad as things tend to get for these kinds of problems, where you end up having to deal with two triangles. Is pretty much as bad as they'll get. Which is like, what did he do? Two triangles. I had to do the Pythagorean theorem twice. I just had to figure out two three-dimensional lines intersect in the last chapter. Woof on that. This is a massive upgrade as far as I'm concerned, right? All right. There's some more parts of this question, though. We also wanted to find the length of EM, where M is the midpoint of this side. So the calculation triangle I drew was EFM. I know EF, that was the height of the pyramid, that was 9.5. FM, we actually know as well. What's the length of FM have to be? 6. Why? Yeah, so why is FM have to be the half of BC? Again, if this is a right square pyramid, which it is, this is like the absolute center of my square. It's like at the centroid, if you remember that term. So I know that it's like equal distant from everything, so it has to be like 6 from each side, right? Everybody's cool with that? Okay. So there we go. Pythagorean theorem. Boom, bada bing. No big deal, right? Everybody happy still? Now notice if I compare EM 11.24 with EC 12.74, they were not the same, right? So why is EC and EM, why are they different lengths? This is what I think is the best explanation. I would say, okay, consider the right triangle EMC. Right? That's a right triangle. M is the right angle. That makes EC the hypotenuse, which you better believe has got to be longer than any of the legs. So they can't be the same length. EC must be longer because of that reason. Also, in addition, like these edge lengths and slant heights are just different lengths. Actually, I think, what do we call? Oh, EC we call a slant edge. And then this would be like a slant height. Anyways, whatever. I like my triangle explanation better than whoever wrote this PowerPoint, which was also probably me, but it was me from like 5 years ago. So, what can I say? Sometimes you get smarter, right? Okay, one more example. Sound good? And we'll be done. Here we got a cone. We're told that the slant height of the cone is 11.3, and the angle of the apex, angle ABC, is 53. And we want to find the radius of the cone. So the calculation triangle I've drawn here is this shaded triangle BDC. So clearly I know that BC is 11.3 also, right? Everybody's good with that? How am I going to use this angle ABC? Well, if I'm talking about the triangle ABC, that's not a right triangle. Oh. So I couldn't use SOHCAHTOA there, although I suppose you could use like a law of sines if you wanted to, or law of cosines if you wanted to. I guess law of cosines would be the one you'd want to use, since that'd be like a side angle side situation. That's a little bit of overkill as far as I'm concerned, but it would work. What else could you do? How about this? Well, how do I know that DBC was half of ABC? What was going on here that allowed Mr. Kulik to just cut that angle in half and be like, good? Not that it was at a right angle at the bottom, although that's, I guess, a piece of it. If this wasn't a height, certainly that option would be out. But not every time you draw a height inside of a cone like that, or inside of a triangle, or is it going to split the angle in half? What else is going on in this triangle? So in the triangle ABC, what kind of triangle is that? Isosceles. That's the reason that the height of the triangle bisects this angle, and it'll also bisect this side length. Everybody's okay with that? If this was not an isosceles triangle, the height of the triangle isn't going to bisect the angle. Have to have the isosceles piece there for that to be true. Everybody's okay with that? I think there was a recent test question where like everybody wanted to like make the height a bisector when like the two sides, when you didn't have an isosceles triangle. Does that sound familiar to you guys? I think in chapter 7 we had a question like that in there. Does that sound right?
The test?
Yeah. I think I had like two people looking up at something, and there's like a flagpole in the middle of them, or in between them, but I didn't say in the middle, and everybody wanted to put it in the middle. It's like, it's not in the middle. It's not an isosceles triangle. You can't just put it in the middle and bisect that bottom piece. Anyways, does that now ring a bell? Yeah. So that again, you got to have an isosceles triangle to do that. But we do. So how can we solve for that radius then? Got an angle measure and a side length inside of a right triangle. SOHCAHTOA. Specifically, which one do I want? I got my angle. I got looking for opposite. I got hypotenuse. Sine. Yeah, so just sine 26 equals r over 11.3. So the radius is 504. NBD, right? It's like, boy, Mr. Kulik, these calculations are like first semester, very beginning of the year type calculations. It's all right triangle. Yeah, can be. You don't have to do like three-dimensional distance formulas. You can just do like regular old right triangle stuff. And that's it for my examples. So for you guys, I think we can do up through, I didn't write it down yet. Let me look up it again. I think through number 7. So 1 through 7, we covered the first 2 sections. Next time in class, we're going to cover the last 2 sections, and then we're going to leave for break. What do you suppose is going to happen before we want to leave for break, though?
Snow day.
What would Mr. Kulik want to do if we're finishing the chapter right before we leave for break? Yeah, maybe. Maybe. I would definitely want to have done those first 7 questions before next time. Like, we'll give you a chance to ask about them or whatever, but probably want to have done that if you're usually I'm going to put it all off to the weekend. It's 7 questions, though, Holmes, and we got like a half an hour or more still left right now. That's not so bad.
Brain is fried.
Me brain, no work.